We're here live in Washington, D.C. Today, we have not one, but two scientific findings for you about oceans beyond Earth. We'll be going coast to coast and ocean to ocean to talk to experts, starting from people right here in Washington, D.C., and then also going all the way to the West Coast to talk to NASA's Jet Propulsion Laboratory in Pasadena, California. And then we're going to go all the way to the East Coast to talk to NASA's Goddard Space Flight Center in Greenbelt, Maryland. Today's panelists are Thomas Zurbuchen, Associate Administrator for the Science Mission Directorate; Jim Green, Director of Planetary Science; Mary Wojtek, Lead Scientist for NASA's Astrobiology Program. The panelists at JPL in California are Linda Spilker, Cassini Project Scientist; Hunter Waite, Cassini INMS Team Lead with the Southwest Research Institute, or SWIRI, in San Antonio, Texas; Chris Glein, Cassini INMS Team Associate, also from SWIRI. And joining us from Goddard in Maryland, we have William Sparks, astronomer and lead author of the Hubble findings with the Space Telescope Science Institute in Baltimore. The news today can be found at www.nasa.gov and also the following web pages. If you'd like to ask a question via social media, please use the hashtag AskNASA. And with that, Thomas, can you kick us off?
Hey, thanks so much, Felicia. It's another great day of science at NASA here. And in the Science Directorate, we really focus on three objectives. The first one is to understand and to improve life on Earth. We also do fundamental research from here to the depth of the universe and understand processes we've never understood before. And the third topic is one that this is all about, which is about a fundamental question that has filled the thinking of so many in the past, and we can answer now, hopefully in the near future, and that is there life elsewhere? See, here on Earth, there's a number of things that help life. There's water in a liquid form. We have an atmosphere, we have a magnetic field that protects us from the hazards of space. There's many things we have going for ourselves. So the question whether there's life out there relates to questions that we're making progress with all the time, and questions that we have, new questions that are coming forward. We don't know yet whether there's life out there, but right now we're making a lot of progress, especially the outer solar system. So this is exactly what today's stories are all about. With this research, we're making a big step forward towards answering the question, is there life out there? And with that, I'm really turning it over to the team. Go team.
Thank you, Thomas. So NASA's strategy for searching for life in the universe begins at home, with an understanding of how life emerged and evolved here on Earth and what the limits to life are on this planet. We then project that out onto other places in our solar system to see if we can find habitable environments that could support life as we know it. Just 40 years ago, NASA sent 2 Viking landers to Mars to look for evidence of life on the red planet. At the same time, oceanographers here on this planet, on Earth, were exploring the last frontier, the deep ocean. And during that exploration, they found made an astonishing discovery that changed how we thought about Earth and how we thought about life here on Earth. And that was an incredible oasis of life supported thousands of meters beneath the surface of the ocean, far away from sunlight. And it was supported by the energy produced by hydrothermal activity. Now, this discovery was incredible for here on Earth. It led to investigations of many other vents, hundreds of vents, which is only a tiny portion of the number of vents that must be active here on Earth. But it pointed out a new type of biology supported by chemistry that didn't require sunlight, which meant that we could extend our habitable environments well beyond the reach of our sun, out into the outer solar system, out to the moons of Saturn and Jupiter, as we imagine environments very much like our own hydrothermal vents here on Earth could exist out there. So today's discoveries have to do with ocean worlds beyond our own planet. And Jim's going to tell you about the missions that brought this to us.
You know, it really began in the late 1990s with the mission Galileo. Galileo, orbiting Jupiter, was flying by the individual moons, the Galilean moons, making observations of the atmosphere and many things in that solar system, that mini solar system. What it discovered from its magnetometer as it flew real close to Europa was a magnetic signature that's very familiar with our scientists because we interpret it as a current within an ocean underneath an ice shell. In 2005, Cassini, orbiting Saturn, flying by the moons of Saturn, with close flybys of Enceladus, it observed huge plumes of water emanating from cracks. We now believe that Enceladus also has a huge ocean. We call these bodies, and many others that are like them, ocean worlds. They are protected by an ice shell, much like our atmosphere protects us, our life here on Earth, and our ocean, maintaining its liquid. This is truly an exciting time for us to be able to probe those and really try to understand what's happening in these ocean worlds. What we're going to talk about today are two really wonderful discoveries, continuing back to Cassini, which has always been one of the major missions that we have, making a huge number of discoveries. And we're going to talk about Enceladus and what it's found out. We're also going to talk about Hubble observations back to Europa. These two ocean worlds we're going to link together because they're so similar in many, many ways that I hope you'll see as we go through our discoveries today. So without further ado, let's go to JPL and talk to Linda Spilker. Linda, what's Cassini been observing?
Well, thanks, Jim. Well, Cassini has been in orbit around Saturn for almost 13 years, and our unexpected discoveries about Enceladus have been some of the most surprising. Today, we're publishing a paper about our recent findings by Cassini on Enceladus. We've detected hydrogen in the plume of Enceladus. That hydrogen is coming from a hydrothermal vent on the seafloor of Enceladus, going out into space through the plume. And so this is a very significant finding because the hydrogen could be a potential source of chemical energy for any microbes that might be in Enceladus's ocean. So this is a very exciting finding for the Cassini team. Now, Enceladus is too small to have retained the hydrogen when it formed. And so the hydrogen we see today, the hydrogen gas, is coming from inside Enceladus. So let's take a quick look at some of Cassini's past findings. With this first image, this is a view of the south pole of Enceladus. And the geysers or the jets are coming from those four cracks we nicknamed tiger stripes, those bluish fractures that you can see at the south pole of Enceladus. In the next picture, you can see that these jets are shooting out into space, forming the giant plume around Enceladus. Underneath that icy crust, as Jim said, there's a global ocean. That global ocean sits on top of a rocky core. And some of Cassini's findings pointed to hydrothermal vents, basically hot water coming out after it's been mixed with the rocky core. And this final image shows a thermal map, the temperature of the South Pole. We can see the warmest temperatures with the yellow and red are right along the tiger stripe fractures. So what's new today? The new finding is finding hydrogen coming from the plume of Enceladus and the fact that it could support potentially microbes with energy on the seafloor of Enceladus. Now, this finding is the result of 12 years of Cassini investigations, and it really represents a capstone finding for the mission because we now know that Enceladus has almost all of the ingredients that you would need to support life as we know it on Earth. Well, here I have a model of the Cassini spacecraft, and Hunter, maybe you can show us where your instrument is that detected the hydrogen.
Yes, Linda. The INMS instrument, the ion neutral mass spectrometer, is sitting on the fields and particle platform right here. And it directly samples the gas that comes in as we fly through the plume, as opposed to an ultraviolet spectrometer or an infrared spectrometer, which would look for scattered absorbed or emitted light coming from the molecules in a faraway location. So this sampling is extremely important for detecting trace species. And we were able to, from previous flybys and previous measurements, find out that the plume is 98% water. It has traces of ammonia, carbon dioxide, and methane, as well as some organics. Now, the part that had been elusive to us before was the hydrogen. And so let me back off here and pick up a similar model. We have a simulation here of the Enceladus and the tiger stripes. And so let me fly my spacecraft with the INMS pointed in the direction of motion of the spacecraft through the plume material, sampling the gas. This is how it happened when we were making measurements. It was about 8 kilometers above the surface, and this happened in October of 2015. It's interesting to put this together with the other measurements we'd made of the composition to try to draw some inferences about what's going on in the interior of the ocean, because this material is telling us about composition of the ocean.
Well, Hunter, what was going through your head when you looked at the data and you saw hydrogen?
Well, of course, we were very excited because we'd been planning this for quite a while, and we've been thinking about what possible applications might be. So to discuss that, let me turn over to Chris and let him talk a little bit about that.
Well, Linda, our team considered numerous possibilities, and after performing a detailed geochemical analysis, we found that the best explanation is that the hydrogen is produced by chemical reactions between warm water and rocks. Here's a graphic showing what we think is going on. We think that hydrothermal fluids are circulating below the ocean floor on Enceladus. This exposes rocks to warm water, which drives geochemical transformations. An important process that produces huge amounts of hydrogen is called serpentinization. In this process, certain minerals that are rich in iron react with water to form new minerals, and hydrogen is produced. This is important because it shows that the geochemistry acts on Enceladus. In addition to this, we think that these warm hydrothermal fluids contain dissolved minerals, and when these minerals mix with the ocean water, which is cold, mineral precipitates form at the sea floor. These mineral precipitates on the Earth form white solids, so we call them white smokers. Here's a video showing an example of one of these systems on on the Earth. We don't know if the systems on Enceladus look like this, but this is an example from the Earth. These vents on the Earth support teeming communities of organisms anchored by microbes that feed on chemical energy rather than sunlight. An important reaction at the base of the food chain is called methanogenesis. This is where microbes combine hydrogen with carbon dioxide to make methane, and they get a jolt of energy out of the process. They use this energy to synthesize some of their complex biomolecules, such as sugar molecules. What is intriguing about the data at Enceladus with the hydrogen detection is that we are now able to determine how much energy would be available from the methanogenesis reaction at Enceladus. We have made the first calorie count in an alien ocean. This is a key step towards understanding the habitability of Enceladus.
Well, Chris, do you think there could be microbes or even shrimp in the ocean on Enceladus?
Why, that would be wonderful, Linda. But we haven't discovered evidence of organisms on Enceladus. But I'm encouraged by the geochemical data, which could allow for this possibility.
Well, thank you very much, Hunter. Thank you, Chris. Well, when Cassini was first built, we never thought we would see an active ocean world like Enceladus at Saturn. So Cassini can look for habitability, but we don't have the instruments to look for life. We've come as far as we can go, so it remains for a future mission to detect life at Enceladus. And the Cassini team is so excited about these new findings. And so, Mary, why don't you put this in a broader context for us?
Thank you, Linda. Well, first of all, Chris, I recognize that footage from one of the NASA researchers, Chris German, exploring the East Pacific Rise, which was actually a hydrothermal system very close to the original observation 40 years ago at the Galapagos Rift. So while we don't understand what the structures would be, and there may be no way for us to tell remotely until we actually get into these oceans, certainly this finding suggests that there's a significant amount of hydrothermal activity to produce such a strong signal of hydrogen. And this hydrogen is a good source of chemical energy to support life. Now, what else have we been thinking about that life needs? So I have a figure here to go over sort of the triad of what we need for life. So can I have the figure, please? So of course, you know that we need water, and here we are at Ocean Worlds. So we have the water. We need chemical elements that can make the building blocks that go into making cells and provide molecules for metabolism. We need carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which are down in the lower left of the triangle. And here we get to check off another box. We have found energy to support life. Hydrogen gas provides that energy. Now all we need is to see if Enceladus had enough time, or any of the other systems in the Saturnian or Jovian world had enough time to evolve life and have life make its imprint on its ocean. So now we have another observation that kind of connects the worlds and is related to what we just heard about, and Jim's going to tell you about this.
So indeed, the next discovery we want to talk about, which is also coming out this week in our science journals, is from the Hubble Space Telescope. That famous telescope that just keeps on making wonderful observations has actually been observing Europa for many years. So let's go to Goddard Space Flight Center and talk to William Sparks. Bill, give us a little background on what we know about Europa.
Europa is one of the 4 major moons of Jupiter. It's about the same size as our own moon, but it looks very different. It's got a smooth, bright, white surface covered in these dark cracks and red patches. The reason for that, and what makes Europa so incredibly interesting, is that it's thought to be engulfed by a global ocean under a thick crust of ice. In fact, it's got twice as much ocean as planet Earth. If we have a salty ocean in contact with a rocky core and energy from a variety of sources, as we just heard from Mary, we have many of the ingredients thought to be necessary for life.
Your observations from Hubble, what are you now seeing that's important to our understanding of habitability on Europa?
In 2014, we used the Hubble and detected evidence of what are probably water vapor plumes emerging from the surface of Europa. That's important because it could be giving us access to subsurface liquid water without having to drill through miles of ice. In 2016, the new observations that we're just publishing, we saw a similar candidate, almost identical in appearance and at the identical location to one of the 2014 candidates. It's very important in an intermittent phenomenon to establish repeatability. It gives us a lot more faith in the observation. The other thing it allows us to do, given the position of Europa, given the position of the candidate on Europa, is to look with more fidelity at that position and see what else we can find there. If we just look at a map of Europa, we don't see anything particularly remarkable about the exact location of the plume candidate shown by the green ellipse. But